Hi everybody, Cal here with sections 15.1, double integrals over rectangles, and 15.2, iterated integrals. So section 15.1 mirrors the development in section 5.1 from Calc 1. This might be different if you're going from this ebook. It's probably 4.1, and let's double check. No, I'm sorry, 4.2. I guess this would mirror 5.2 if you took Calc 2 here. At any rate, well, now I have lost my page. At any rate, um, we're going to formally develop the double integral in section 15.1. And what your book does first is it reminds you of the construction of the integral in single variable calculus. So do read this section review of the definite integral pretty carefully. And then read this discussion volumes and double integrals over here on the bottom of the page. And I would say that this whole discussion is pretty important. You wanna make sure you understand what's going on. And there's some really good pictures in Figure 4, Figure 5 at the bottom of 999, and there will be some better pictures later on in the examples. Your book talks about finding the volume of a solid lying under a graph, and it talks about the double integral for a function f over a rectangle as the limit of a Riemann sum of a Riemann sum. That's a lot of notation to wade through, but the picture that's going on is this one on the previous page. We're dividing our rectangle R into a bunch of sub-rectangles and putting a column over each one, taking the volume of each, because we know how to take the volume of a rectangular prism. Your book does all the formal definitions on page 1000. And I mean, this is good stuff to know. You don't have to take most of this stuff too terribly seriously. And I'm not going to be asking you guys to cook up any or evaluate any double Riemann sums. I'm more concerned that you understand what's going on in these examples here. So I really like example 1. I really like the discussion below example 1. I want you to read that and make sure you understand the pictures here. Example 2 is a pretty good one, evaluating a double integral by interpreting it as volume. I like this discussion of the midpoint rule. Maybe not as much as it is presented in example 3, but I really, really like example 4, which uses the midpoint rule and goes into this idea of average value. So do read the average value thing. That's relatively useful. On the previous page, there's this nice note at the bottom of 1002. Again, talking about the interpretation of the double integral as a volume and what it means when it's not a volume. Anyway, example 4 is a great example. It goes from 1003 to 1004. Make sure you understand what's going on in that example. It's pretty great. If you can follow what's going on there, then you're pretty much on top of this section. And then at the top of 1005, the book goes over some basic properties of double integrals that, if you're used to single integrals, then these should not be a shock. So there's not a heck of a lot to this section. For the most part, I want you to read this, make sure you understand a couple of things, especially, example 4 and some of the pictures in here. And then you can move on with your life. Sorry, missed it. At the bottom of 1006, we get into section 15.2, iterated integrals. And your book starts by presenting iterated integrals. It's basically an integral with respect to one variable inside an integral with respect to another variable. I really like the comment on the top of page 1007 about partial integration with respect to a variable and its similarity to partial differentiation. Make sure that you can do the stuff in example 1. That's certainly well within your abilities at this point. Now, after example 1, your book goes into a discussion of what's called Fubini's theorem. And to a certain extent, Fubini's theorem, it's what relates double integrals, on the left here, to iterated integrals, things that we can actually compute. it's similar in importance to the fundamental theorem of calculus back at the tail end of Calc 1, where we related this formal object, the integral, to a process antiderivation that we could actually do. And Fubini's theorem is the same kind of thing for us. It says that the double integral is equal to the iterated integral in whichever order you like. You could integrate with respect to y first or x first, and that's going to be really important. I really like these pictures in Figure 1, Figure 2, and the discussion here of why Fubini's theorem should hold. There isn't a proof of it in this book because the proof is actually pretty difficult, but I really like this discussion at the bottom of page 1008. Going onward, examples 2 and 3 are both pretty good ones. I really like that they demonstrate that the order of operations in your integrals don't matter, and that you can choose whichever one is going to give you an easier integral to work with. That's pretty important. And example 4 is more of the same. I would more or less ignore the stuff that comes after example 4 in this section. I'm not going to say that it's never useful, but it doesn't come up that often, and I just wouldn't concern yourself about it that much. It's nothing you really need to know. So that's it for section 15.1 and 15.2.